Dear students, after studying this module, you shall be able to know what are ambident nucleophiles, learn about the mechanism of ambident nucleophilic substitution, identify factors that decide point of attack by ambident nucleophiles, evaluate various types of functional groups as ambident nucleophiles, and analyze regioselectivity because of ambident nucleophiles. Introduction. A nucleophile is a chemical entity that donates an electron pair to an electrophilic center to form a chemical bond. The terms nucleophile was derived from nucleus and a Greek word philos, meaning love, and was coined by Christopher Kelk Ingold in 1929. All molecules or ions that can donate a free pair of electrons or have at least one pi bond can act as nucleophiles. A nucleophile can have more than one atoms carrying a pair of electrons, or the electrons may be shared by two or more atoms, so that canonical forms can be drawn in which two atoms bear an uncharged, unshared pair of electrons. If such is the case, the nucleophile may attack in two or more different ways to give different products. Such nucleophiles are called ambident nucleophiles. Now, this word ambident comes from ambi, which is from the Latin language meaning both, and dent again comes from the Latin language for teeth. That is why ambident nucleophiles are those which can attack from both the sides. According to the IUPAC nomenclature, ambident nucleophile consists of two or more alternative and strongly interacting distinguishable reaction that occurs at either side. It generally stops or greatly retards a subsequent attack at the other sides. A common example, students, of ambident nucleophile is the enolate ion with oxygen and carbon as two nucleophilic centers. Now, here you can see that the enolate ion has the charge distributed over the carbon as well as the oxygen center. Thus, it behaves as an ambident nucleophile. A nucleophile with two potentially attacking sites can exhibit a dual reactivity by attacking with either the electron rich center or the other side. There are various factors that decide which atom of an ambident nucleophile will attack a given substrate under a given set of conditions. That is, if the kinetically controlled product will predominate or the thermodynamically controlled product will take place preferentially. Therefore, depending on reaction conditions, ambident nucleophiles generally lead to regioselective reactions. That means the reactions where formation of two or more constitutional isomers can take place, but actually only one regioselective product is formed. By constitutional isomers, students, I mean like ROCN or RNCO. They basically have the same molecular formula, but their functional groups are different. Structures of some of the important ambident nucleophiles can be shown to be resonance hybrids, as like you can see here, there are various ambident nucleophiles that we have shown you, and their structures and their canonical forms or the resonance stabilized forms, making them, the charge in them being distributed over two atoms, thus ideal for them to behave as ambident nucleophiles. Now students, let us come to a very important concept in chemistry, that is the hard and soft acids and bases concept and factors influencing ambident reactivity. Which end of the ambident nucleophile should react predominantly under a particular set of reaction conditions? Now, to answer this question, two most important factors are to be considered. First one is the polarizability of the nucleophile, and the second is the nature of solvents. Now, I will take these two factors up in detail. The first factor, students, was polarizability of the nucleophile. To explain the ambident character and polarizability of the ligands, the principle of hard and soft acids and bases, that is HSAB principle, was used. According to this principle, hard acids prefer hard bases and soft acids prefer soft bases. This is based on experimental calculation of enthalpy involved. Now, for an ambident nucleophile, the more electronegative atom is the harder base, then the less electronegative atom. Thus, in an enolate anion, like discussed before, the more electronegative oxygen atom with a negative charge is a harder base than the carbon atom carrying the same negative charge, which is distributed among these two atoms. The table here classifies the common organic ligands as hard and soft acids and bases. Now, let us have a look at this table. Now, there are hard acid cases, there are soft base cases, and there are borderline bases also. So, hard bases are the ones in which the donor atom has high electronegativity and low polarizability. For example, we have water, hydroxyl ion, fluoride ion, acetate ion, sulfate ion, and the ether ion, RNH2, that is the primary amine, ammonia, alcohols, that is aliphatic alcohols. Soft bases. What are soft bases? Donor atoms having the low electronegativity and high polarizability can be put into the class of soft bases. For example, we have R2S, that is the thioether, RSH, that is the thioalcohol, iodide ion, cyanide ion, the alkyl cyanides, we have the alkenes, and we have benzene. Borderline bases, that means these neither lie in the soft base class or the hard base class. For example, we have the arylamines, the azide ions, the bromide ions, and the NO2 minus ions. Now students, let us go to hard soft acids and borderline acid cases. Hard acids are the one which have small acceptor atoms and have high positive charge without an unshared pair of electrons. For example, you have the hydrogen cation, you have the lithium cation, the sodium, potassium and magnesium cations, the calcium cation, you have trifluoroborane, you have aluminum chloride, aluminum hydride, and SO3 and RCO plus cations. In case of soft acid students, they possess large acceptor atoms and have low positive charge, and they contain an unshared pair of electrons. For example, you have copper 2 plus ions, that is the cupric ions, the Ag plus ions, that is the silver plus ions, the palladium ions, the platinum 2 plus ions, mercuric ions, and the BH3, that is borane, the iodine and the bromine. Then you have the borderline cases which are neither lying in the hard acid class nor in the soft acid class. They are the ferrous ions and the cobaltous ions, the cupric ions again, the zinc ions, the bismuth ions, and the trialkyl carbon, the NO plus, and the C6H5 plus, that is the phenyl cation. Now for SN1 mechanism, a carbocation intermediate is a hard acid that would prefer attack by a hard base, that is attack of oxygen of enolate. On the other hand, for SN2 mechanism, the carbon at the reaction center is a softer acid and would preferably get attacked by a carbon atom of the enolate ion because that is a softer base. This was generalized as the character of a given reaction changes from SN1 to SN2, like an ambident nucleophile would more likely attack with its less electronegative end. So I hope now you have understand the polarizability concept. Now coming to the second factor, which is the nature of solvent. The nature of solvent has been shown to guide the position of attack in a number of reactions for ambident nucleophiles. In protic solvents, through hydrogen bonding, the more electronegative atom is better solvated than the less electronegative atom. Thus, less electronegative atom is more prone to attack. In contrast, polar aprotic solvents offer no stabilization to either end of the nucleophile. However, they stabilize the substrate cation by solvation. As a result of this, the more electronegative end of the nucleophile is more free, so the extent of attack by electronegative atom increases. As an example for the reaction, under different solvent conditions like shown in table, the ratio of N-alkylation to C-alkylation changed dramatically as shown by the proportion of products formed in this reaction. Now you have this cation, the pyrrole cation, the potassium cation of pyrrole, and you have this reaction here. Now considering this reaction, if you have the solvents, let us say, and the formation of products A and B, you have first solvent as tetrahydrofuran. The percent of A will be 81:19, with dioxane it is 71:29. However, if you notice for diisopropyl ether, you have 21:79, that means 79% of B is forming. So, as you go on to ether compared to furan, the percentage of B is increasing. In benzene, the percentage of B is even more, that is 85:15, 85% of B and 15% of A. In toluene, 1% also increases then from benzene, that means A is only 14%, however, B is 86%. In N-heptane, it is A is 14% and B is 86%, again the same case as in toluene. The leaving group and counter positive ion of the nucleophile also influences mechanism of reaction and therefore influences the major product which is formed. For the alkylation of 2-hydroxylpyridine, that is the enolate ion of 2-hydroxylpyridine, when the reaction was carried out with potassium ions as the counter ion, a SN2 mechanism was favored and the soft reaction center nitrogen atom participated in the reaction, giving 73% yield of the product. Now you can see here the two similar reactions of pyridone, that is the enolate ion of 2-hydroxylpyridine. First one with potassium ion will give you 73% of yield. However, the SN2 mechanism. However, students, if you look, if we are using the silver cation, then SN1 mechanism will prefer in case of pyridone. On the other hand, if instead of K the counter ion is silver cation, then due to the ability of Ag plus, because it is a softer acid, to coordinate with the leaving group iodide ion, which is again a softer base, the reaction was found to favor SN1 mechanism and therefore O acylation product will be 80% in yield, was obtained thus as a major product. Now steric hindrance at the nucleophilic center may become predominating factor to decide the point of attachment wherever it is applicable. For example, the alkylation of phenol with alkyl iodide gives O-alkylated product. Now this is clearly seen here in this reaction with the phenoxide ion and the 2,6-dimethyl phenoxide ion. However, if you see when the reaction is crowded, just like I said in 2,6-dimethyl phenoxide ion, the para-alkyl substituted product leading to C-alkylation is favored over the O-alkylated product. Now students, taking up the next topic after having discussed the two factors is the reaction mechanism involving ambident nucleophiles. Let us consider now Neph reaction. Neph reaction involves conversion of a nitro compound to carbonyl compound through a nitronate anion. The nitronate anion is an ambident nucleophile which can either attack from the carbon end acting as a soft base or from oxygen end acting as a strong base, that is a hard base. The reaction goes by attack from the carbon end predominantly as follows. Now you can see this reaction here, it goes predominantly from the carbon end, that is a softer base. However, if you consider the reaction, O-alkylation is possible if a hard alkylating agent such as MEO-SO2F as an agent is used. Thus the reaction would proceed like this, that means the attack by the harder end. Consider the Kolbe-nitrile synthesis. The reaction of primary aliphatic halides with alkali metal cyanides gives nitriles in a good yield. Now see this reaction of the alkyl halide reaction with potassium cyanide in DMSO, it will give you a cyano-substituted compound, that is alkyl cyanide. The mechanism is as follows. However, since the cyanide is an ambident nucleophile with both the negative charges spread around nitrogen as well as carbon in the reaction, attack from the nitrogen end of the nucleophile results in the isocyanide product as follows. Now you can see The attack on the carbon is from the nitrogen end of the ambident nucleophile, that is cyanide ion. The nature of cation here plays an important role as isocyanides are formed with silver cations and cuprous metal cations. Compounds with active methylene group such as acetylacetone can be alkylated at either the carbon, that is C alkylation, or at the oxygen O alkylation atom through an enolate anion. It was reported that the value of O or C alkylation ratio depends on the polar effect of the substituent, the steric effect of the alkyl groups and the nature of the leaving group. When the leaving group is a soft base, that is iodide, bromide, chloride, etc., the steric effect predominates, the O by C ratio decreases in the order of like this, as you can see, and the alkyl group sequence opposite to the order given above operates for the hard leaving groups. The reaction between nucleophiles and polynitroaromatics has been a focus of a lot of mechanistic studies. This is because of the possibility of isolation of an intermediate or transition state and the diverse number of products formed such as pi complexes, radical anions, radicals and anionic sigma complexes. The phenoxide ion is an ambident nucleophile. When reacted with 2,4,6-trinitrobenzene, both O and C alkylation products are possible. The attack by C6H5O-, that is the phenoxide ion, through oxygen end was found to be reversible and kinetically preferred, as the formation of C adduct would not lead to disruption of aromaticity of the ring which is involved here. Now, as you can see here, the reaction of 2,4,6-trinitrobenzene with the phenoxide ion and how the reaction proceeds. However, the C bonded adduct once formed rapidly aromaticized by proton loss to give the final product. Therefore, this pathway was found to be effectively irreversible. The C bonded adduct was therefore obtained as a product of thermodynamic control. Now students, let us talk of a very important concept, that is the regioselectivity. Many reactions have strong preference for forming only one regioisomer over the other possible isomer. This property is known as regioselectivity. The subject has been partly covered in the earlier modules dealing with ambident nucleophiles. In this module, we shall illustrate regioselectivity with some good examples. Let us first consider the alkylation of ketones as an example of regioselectivity. If unsymmetrical ketones are there as shown here to you, they can be alkylated either at the alpha position or at the position depending on the experimental conditions. The methodology consists of steps shown in the reaction. Now you can see how the reaction is proceeding in case of different reaction condition. Here it is a base solution and the methyl iodide, and what are the kind of products or possibilities of products which are there. The first reaction is deprotonation on alpha or alpha dash position, that is, which is an acid base reaction, and the second reaction is an SN2 reaction. Carbon ion is the nucleophile and CH3 is the electrophilic agent in case from the methyl iodide. In point of fact, the two new products are not formed in equal amounts. If A is the major C alkylated compound, we say that the reaction is regioselective alkylation. Alkylation of ketones via carbon ion of its equivalent enolate is a very important topic of very wide scope. Now you can see here in this reaction, the concept of regioselectivity can be best illustrated with some more selective examples, like first is the bromination of acetanilide. Here you shall see in the bromination of acetanilide that para is the major product. 4-bromoacetanilide or para-bromoacetanilide is the chief product. Ortho and meta products are negligible. This is regioselective bromination. Again, coming down to the hydroboration. The addition of borane to a double bonded or triple bonded group to give an organoborane is known as hydroboration reaction. Now, the mechanism involves a concerted 4-member transition state. The boron always combines with the carbon of the double bond, that is less substituted. This is another example of regioselectivity. Third example is the Diels-Alder reaction. Regioselectivity in cycloaddition reaction such as the Diels-Alder reaction, can be observed here. Here you can see only one kind of product is formed, not the other. So thus Diels-Alder reaction is a great example of regioselective reactions. Hydrogen halide addition to an alkene is another example of regioselectivity. Consider the hydrogen bromide addition to methyl cyclohexene. It is a regioselective addition to give only 1-bromo-1-methyl cyclohexane. The fifth example is the ring opening of epoxides. Epoxides are very useful intermediates in synthetic organic chemistry. Epoxides are readily prepared by treatment of an alkene with peracids, or called the epoxidation. This reaction and its subsequent transformations have been extensively studied and documented. Epoxides contained 3-membered strained ring. It is subjected to ring opening in two ways, either it is acid catalyzed or base catalyzed. The first process, that is the acid catalyzed, starts with attack by an acid, that is H plus hard acid, or the Lewis acid at oxygen, and the second process is base catalyzed, that is a nucleophile or a base, attacks one of the carbons from a SN2 mechanism. The topic of regioselectivity in epoxide opening there is very important. In general, nucleophiles attack at the less highly substituted carbon of the epoxide ring in neutral or basic media as expected from the SN2 process. In acidic media, however, the proportion of attack at more highly substituted carbon is increased and may become the predominant form of reaction. Study the example carefully. You will get the answers to what the above statements mean. Now you here have to ignore the stereochemistry for your convenience. Now let us see the acid catalyzed methanolysis of epoxide and the epoxide ring opening under SN2 and acidic conditions. If you carefully see these reactions, you will always appreciate the regioselectivity in case of the ring opening of epoxides. Students, now we shall summarize this module. In this module, we have tried to explain you that an ambident nucleophile is a nucleophile that can react at more than one site. Ambident nucleophiles generally carry heteroatoms with lone pair of electrons or pi electrons and exist as resonance stabilized structures. Reactions of substrates with ambident nucleophile generally lead to regioselective reactions, where one constitutional isomer is favored based upon the reaction conditions. In a reaction, the polarizability of nucleophile according to the HSAB principle and the nature of solvent decides which end of the ambident nucleophile will give rise to the major product. We have also told you that according to the HSAB principle, hard acids prefer to combine with hard bases and soft acids prefer to combine with soft ones. As the character of a given reaction changes from SN1 to SN2, like an ambident nucleophile more likely attack with its less electronegative end. Now at the last we told you that the prediction of regioselectivity in a reaction depends upon the substrate, reagent and the experimental conditions. Now students, these topics are very important for organic chemistry and I hope you found this module very informative.